So, hey students, and welcome to another session by Quant Masters on WIPRO specific training. So, in today's session, we'll go through a few more concepts that are often asked in round two, that is the live round when it comes down to WIPRO. So, in the last session, just to point out, we went through a lot of concepts from data structures. We looked at all the concepts from data structures, including how questions could be asked from stacks, queues, linked lists, double linked lists, as well as graphs. Followed by this, we went through the concepts of all the applications of the data structure where questions could possibly be asked. And followed by this, finally, we went through of concepts that are on algorithms, particularly on time complexity and space complexity calculations. So we got to know, in short, till now, that whenever we are supposed to calculate time complexity, we never see the number of seconds that the program takes. Instead, we always see the number of operations that the programs take up, number of the operations that our particular program will take up, because number of seconds will change from computer to computer, but number of operations will always remain the same. That is how we calculate something called worst time complexity, which is the most important aspect to analyze and understand how much time does an algorithm take. So one of the common questions you can expect from algorithms is all about time complexity. That is, when it comes down to certain algorithms, like for example, certain sorting algorithms, how much time would it take? Which sorting algorithm takes the fastest time? Which sorting algorithm is better when array is sorted? Which sorting algorithm is worse when array is sorted? We can expect certain questions when it comes down to algorithms. Followed by this, a couple of other questions that you can expect here are on dynamic programming, as well as what is greedy algorithm, and what exactly are divide and conquer, and finally backtracking algorithms. So what are these methods in which algorithms are created? So in this session, we'll look at this, and followed by this, we'll directly move ahead over to the concepts of computer networks and look at the common questions that can often be asked even from that particular subject. So let's go ahead from here and begin without any delay into algorithms, now that we have had a small recap on what we need to know in order to work ahead with algorithms. So the first thing, when we start about algorithms, so as we know, algorithms are just a set of steps to solve a problem in a certain way. Now these set of steps can be performed in many ways, and one of the way is called dynamic programming. So what exactly is dynamic programming? How does it work, and what is the benefit of it, and what advantages of it? So let us start working through this. Let us start looking at all of these. So from short, to speak in short, dynamic programming can be implemented in multiple ways. One of them is called memoization and the other is called tabulation. So the entire concept of dynamic algorithm goes like this. It is, assume any particular program, you would never want to do one task multiple. You want to do one task one time at maximum. So any multiple times is of no use, because you're essentially performing same thing over and so all. We use the concept of dynamic programming, where we perform one task only, same task if it needs it takes up the result when it was performed and the same result is utilized. So how exactly this works so that we can understand how in real cases we can implement such tasks. Now, starting with the first thing, think about as always, we look at questions that can be asked and we try to answer them. So, this question that I would just want to start with here, dynamic programming ensures it's the main task of it is ensure that there are no repetitions of tasks. Every task that is performed should be only once. If the same task again, then there's no point in efficiency. That's the main concept of dynamic programming. To understand this better, I'll just take a simple case. Let's assume I'll just take, let's say, one file. Let's just call it as code.c. And the simple example that I'll take for this is Fibonacci numbers. Now everybody knows how to work with Fibonacci numbers. So you have your function called int fibo of int n. If you want to find nth Fibonacci number, what you really do is take up an integer n if n is equal to 1 or n is equal to 2. If it's the first term or the second term, we basically return the same value. So if it's first term, we return 1. If it's second, we return 2. Let's assume that is the case. So if n is 1 or 2, we're going to return n. Else we'll just perform fibo of n minus 1 plus fibo of n. This is the exact operation we are supposed to perform. Now this sounds simple. We know how this absolutely works. I'll just take one example. Let's say we take up Fibonacci of 5. Let's say we want to find out the fifth Fibonacci number. To do this, I need to first take up plus the third Fibonacci number. So to get fourth Fibonacci number is f of 3, 2. Similarly, to get Fibonacci number, let's say for example, I need f of 2, f of 1. Similarly, for second Fibonacci f of 1 plus f. In this case, assume if 0 is entered or 1 is entered, we'll return other one, return the results. So instead of 1 and 2, this makes a better sense. Let's just return 0 and 1 for now. If n is 0, we are returning n, that means 0 itself. If n is 1, we are returning n, which is 1. So here in this case, we are going to return 1 plus 0. So in this case, again, same thing we have to do with of 2. We're going to have to calculate plus. Now again, if you go ahead here, even again here you have to calculate Fibonacci of 3, which is again Fibonacci 2 plus Fibonacci of 1. Again, Fibonacci of 2 should add it into Fibonacci of 1 plus Fibonacci of 0. Now if you observe, we are calculating Fibonacci of 2 how many times? Once here, twice, thrice. If same task is performed thrice, is it really effective? Is it really efficient? Even think about Fibonacci of 3. Calculating it, we are calculating here and we are also calculating here for the second time. So even here we see that it's not efficient because same task. We know whether we calculate Fibonacci of 3 here or here, the output result will be the same. The third Fibonacci number will not change here or here. So why are we supposed to calculate it twice when we calculate it once? So this is what we do using dynamic programming. In dynamic programming, instead of doing all of this work, what we will do is take, in other words, here let's assume we are taking an array. So we'll take an array which, if we want to find nth Fibonacci number, let's say n is 10, we want to find 10th Fibonacci number. Our array will have length up to 10, 0, 1, 2, 3, 4, 5, 6, 8, and 9. Let's say, for example, like this. So because for me to find f of 10, Fibonacci of 10th, I need to add number and 9 Fibonacci number. That's what I need. So initial two values will 0 and 1. So after this, the next thing that we do is f of 2, the array index 2. So for each array index, 2 will be equal to array of 1 plus array of 0. So array of 1 plus 0 gives you 1. Similarly, the next is equal to array of 2 plus array of 1. So like this, we need to keep on doing until we reach this particular value. So here also, let's say we take it up as 2. Now 1 plus 2, let's say we take it as 3, 2 plus 3, 5, 3 plus 5, 8, and so on. Once you keep calculating Fibonacci of 8, Fibonacci of 9, which you just have to add by the end. That is, you just have to perform of 8 plus a of 9. Now the operations found are much lesser, significantly lesser compared to Fibonacci program that we did without it. So we can see here that this particular program is more efficient in terms of time as well as space. Now, in terms of time and space, see, in your Fibonacci program, how are performed. If we can go through this, if we can go through and calculate how much memory it takes, we'll get to understand that it's a pretty hectic program. In other words, it's taking a lot of time to this. So in our case, even when we talk about this recursive method, again, I'm currently only talking about a recursive method to calculate. We are not talking about the method that we just started to learn. That is, we are not talking about the method that we just got to know with just using a single array. That's not the case. We are not talking about dynamic programming. Instead, we are talking about the recursive method. When recursive method, our equation is Fibonacci of n equals Fibonacci of n minus 1 plus Fibonacci of n minus 2. And this n minus 1 will take time again, and this n minus 2 will take time again, and it keeps going. If you calculate it, how many times a Fibonacci function runs, it runs approximately 2 to the power of n times for a value n, approximately 2 to the power of n. Take this for example, Fibonacci of 5 is 4 plus 3, 4 is 3 plus 2. I'm not using Fibonacci function, assuming that we are able to understand this. Let's just quickly understand how exactly it is 2 power n, and given any algorithm, can we calculate, given any program, how can we calculate time? So we need to always take a larger. For smaller numbers, it may not always resemble the same. So let's take Fibonacci 1, here also Fibonacci of O plus Fibonacci of 0, again even here Fibonacci of 1 plus Fibonacci of 0, and let's take the same thing here, Fibonacci of 2 plus Fibonacci of 1, and finally here 1 plus Fib of 0. Now when we calculate this, once, twice, thrice, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 times. So for a value, we are accessing it 15 times. So when you calculate, it is very when we calculate through the value does not resemble very close to, because when we talk about smaller numbers, it's not close. So for us to understand perfectly, we need to take much larger numbers like Fibonacci of 10 and 11 and 12, because these are exponential programs. For smaller, they may take less number of iterations, but as the number goes larger, the graph becomes exponential. So in this case, this exponential growth of the graph can be identified as 2 to the power of n. So if you want to find nth Fibonacci number, you basically have to perform 2 power n operations at maximum. That is why the worst case scenario is called big O of 2 to the power of n. So going ahead with this is not easy to work through. It's really not easy to solve because it's a very huge time complexity. We measure time complexity always as first will be always constant, like 1, then followed by big O of 1, the more complicated or the complex one are measured as big O of n, then big O of n square, then big O of n cube. So before n and n square there's also big O of n log n, and before 1 and n there's big O of log n. So then big O of power of n and so on. So all of these are there, but the major points we need to know are these ones. So this is the complexity when it comes down to factorial. But when we work through our method, all we need to do is n operations. That's it. So for each value, I'm just supposed to take previous two values and add. So at maximum, I'm taking only n operations, because if I need to calculate fib of 10, storing 10 values, I'm performing at maximum 10 operations to find each value, no more than that whatsoever. So only 10. So we went from a time complexity, worst case time complexity of 2 power n, all the way over to a worst case time complexity of just n. That is how you can reduce repetitive tasks and utilize dynamic programming as effectively as possible. There is a point here. So in our case, if we would want to create a program to do that, all that we would need to do is just take void main, given an input n. I'll just take this program up quickly, so that in case they do ask dynamic programming, because smaller programs you may expect, larger programs short time face-to-face interviews, I highly doubt that you expect, but smaller programs you may. So it's good for us to know. Let's say void main, and we'll take an int n. So if user wants to say, for example, enter a value of n, let's say n equals 10 or something like that. So you need to create an array of 10 elements. Here's the basic thing we need to know. If I need to calculate fib of 10, I need to get fib of 8, know fib of 7 and fib of 6 and fib of 5 and so on, and it comes down to fib of 0. So this is 0 to index 9, so that basically is 10 elements. So in this case, we can create such an array size dynamically by just using malloc of size of int into n. So whatever is the size of integer in the system, it could be 2 bytes, it could be 4 bytes, that we are multiplying with n to retrieve so much memory from memory manager. So once that much memory is retrieved from the memory manager, we will then be utilizing it, converting an integer pointer from a void pointer and storing it to something like p, where p will be an integer pointer. Now all that we would need to do here is just have a formula where p of 0 and p of 1 is equal to 1. Now you just need to do a loop for I equals 2. We'll also create one more integer called I. Let's say for I equals 2, I less than n. So until I reaches 9, keep on increasing. You just need to do p of I equals p of I minus 1 plus p of I minus 2. Once you keep calculating, whatever are the final two values you get, that is what you need to add. So you just need to print the final result, that is percentage d slash n, comma, p of I minus 1, p of I minus 2. That's basically it. Sorry, not I minus 1, n minus n minus 2. Now, this seems like simpler and much easier program of recursion to see that you're performing the tasks again and again. This is how you can realize or can start to think, figure out. We can write it this program in a month by ensuring that we use dynamic programming. Again, the main repetitive basic is the basic rule. Now, the other question you can possibly on sorting algorithms. Now, of course, they will not ask you to create sorting algorithms. They'll just ask you, what are the sorting algorithms you know, and what do you know about them? So, if we go through this, there are a lot of sorting algorithms that we can start learning from basics. That is, you have bubble sort and selection sort. I'll explain why I'm putting these three in C. Followed by this, you also have merge sort, heap sort, and quick sort. So let's take a look at what questions you can possibly expect from these. So the first question and the main question that I would state that you can expect from any of these is time complexity. So the time complexity for these three, worst case time complexity for bubble sort, insertion sort, and merge sort, are always n square. So the basic point we just need to know for these three, it's always n square, which is the worst time complexity. So followed by these three. When you talk about the rest, merge sort, heap sort, and quick sort, they work on a very different way. They work on a very different basis. So the idea here is merge sort and heap sort both take very similar time complexity. Both of them take the time complexity that is n log n. Followed by this, the final thing that you have is quick sort, which is a divide and conquer approach, and this takes a special time complexity, which I'll explain in just a little while. But before going on to quick sort, let me just point out a couple of things. When we talk about algorithms, the main thing that is asked often is worst case time complexity. So when we talk about worst case time complexity, each algorithm works in a different way. So I'll just point it out. There are two common algorithms that you may expect when we talk about time complexity as questions. One is searching algorithm, the other is sorting algorithm. So for searching algorithm, we have gone through a few programs earlier on, which we have learned through. But let us go through sorting algorithm and look at what works in what particular. So here's the basic idea. So to begin with, the first thing is let's go for selection sort. Now, I will not go in depth within it because you will not expect much questions in the coding of this, whereas the major steps you will expect is questions based on time complexity when it comes down to algorithms. Which algorithm will you use in what way, or what do you know about a certain algorithmic technique? So that is why I'm not going to go in depth much about this. So here's basically how selection sort works. It selects the minimum value in each pass. In each pass, it will always select the minimum value, and it's going to sort the array in that way. So in the first pass, if let's say an array is 10, 11, 7, 9, and 3, whichever is the minimum value, that minimum value is what it tends to find, and it selects it and puts it at the start of the array. Then it selects the second minimum value, puts it at the second element, third minimum value, puts it as the third element, fourth minimum value, puts it as the fourth element, then fifth value, whatever is left, the last value, that will be it. So this is the basic idea of it. And since you're going to use one for loop within another, we generally take it up as n square. That is, worst case time complexity is considered to be n square over here. Whereas on the other hand, when we talk about bubble sort, bubble sort works based on adjacency sorting. So it takes every two element, let's say A and B. If they are not sorted, it's going to sort them, then go to the next two elements, B and C. If they are not sorted, sort them, then it goes to the next two elements, C and D. If they are not sorted, sort them, then it goes to the next two elements, let's say D and E. If they are not sorted, sort them. By the end, even if the highest, largest element at the start, like let's say 10, 9, 8, 7, 6, since we are sorting these out, it's going to become 9, 10. And since we are sorting these out, it's going to become 8, 10, because 10 was here earlier. Now, since we are sorting 10 and 7, it's going to become 7 and 10. Now, 10 and 6, it's going to become 6 and 10. So, the highest or heaviest element will go to the end of the entire array in each pass. So, after that, then it takes up only the values before that. So, this is basically how it works. Now, it doesn't exactly take big O of n square, but it's very close to it. That's why we generally consider it as big O of n square. So this is basically how selection sort and bubble sort work. Now, followed by this, the next thing is insertion sort. So insertion sort works also in a similar way, where you have to iterate all the indices comparing a value to its previous value. So let's say, for example, if let's say we have 4, 3, 2, and 10. First element is compared with the previous element. Since it is lesser than it, we'll swap it. Then next element, whatever it is, that is compared. If it is lesser than all of these, put that up, then it becomes 2, 3, 4. So this is how we basically start sorting it. So whatever is element is there, just keep putting it in its place in each step. In each step, you insert the element in its rightful place. So 3 was inserted in its rightful place in this step. 2 was inserted in its rightful place in this step. If instead of 2, let's say, if instead of 10, if this was, let's say 1 would have been inserted in its right step in the last stage. So like this, in each step, the element is inserted in its right place and so on. So this is basically how it works. So similarly, you have many others like quick sort, radix sort, and so on. So the most important thing that we need to know when it comes down to these is there are different kinds of sorting techniques. In your interviews, they may ask you what is in place. What is in place sorting? And what is stable sorting? So let's just take a look at what these are. What is exactly in place sorting and stable sorting? So in place is where if you do not use any extra memory in the program, it is called in place sorting technique. That is, you're sorting within the place given to you. You're not taking extra memory whatsoever. So most of the initial algorithms are in place, but the few techniques which don't use in place. For example, I'll give you one example. When you talk about merge sort, as the name says, it takes up two arrays, two sorted subarrays, and merges them by the end. So since it takes two subarrays, it requires extra memory to store things out of the place. So this is one example. Similarly, when you use a hash table for sorting, some algorithms also use hash table for sorting, such as counting sort or bucket sort. So when these use external memory also, they are also not part of in place sorting. So merge sort, counting sort, and bucket sort are not part or not examples of in place sorting. Followed by in place sorting, the next thing is you have something called stable sorting. Now, how do you define what is stable and what is unstable when it comes down to sorting? It's kind of like a little confusion. So the idea is a sorting technique is stable if it doesn't change. I'll just repeat, if it doesn't change order of elements with the same value. When multiple elements are there with same value and it doesn't change the order, it's called stable sorting. That's the basic idea about it. So with these two known, you can see that there are certain unstable sorting as well. Unstable sorting algorithms are, for example, quicksort and heaps. Both of these are considered to be unstable sorting methods. Now, let us move on from this. Let us go ahead and let us look at the possible questions you can expect from here. So first, I'll just take this example for your reference. This is for Fibonacci numbers, an easier program using dynamic programming. Followed by this, let's look at values. That is worst case time complexity for sorting algorithms. So in take, for example, bubble sort. I'll write two things over here. One is worst time complexity and space complexity. Space complexity only in terms of extra space is required to store the array. Whatever is required to store the array will not consider it here. Only extra space is what I'll be considering over here. Now, when we talk about bubble sort and insertion sort as well as selection sort, we know that all three of them have the worst case complexity of big O of n to the power of 2, big of n square, because both of them have one loop within the other and they almost go up to number of operations as n square. It's not exactly n square, but it's very close to n square. So followed by this, the next thing is space complexity. Now, apart from the array, we only need one extra space to store one element to perform swapping, because bubble sort, insertion sort, and selection sort work based on swapping. Because of that, we only need extra space to work through. So that is what we'll take it up. That is big O of 1. So followed by this, let's go on to the next part. And heap sort and quick sort. Now all these three algorithms are pretty similar in their time complexity. Three of them take the short possible, that is n log n. N log n is always lesser than n square, because log n is much lesser than n square. So take this as n log n. So for those who don't know how log works, I'll just give one example. Take 2 to the power of 5. This gives you 32. So if I want to get this number, all I need to do is log 32 to the base 2. So this will give me 5 because 2 to the power of 5 gives me 32. So log n base 2 is much lesser than n. It is so much lesser than n, so that big O of n log n is more closer to n in a number table. When it comes to a number table, it's more closer to n than n square. It is more closer to n. So that is why I can consider this takes much lesser time compared to the previous algorithms. And when we talk about space, to perform merge sort, we need to divide the arrays to subarrays. That will take exactly n spaces. But when we talk about heap sort, we don't need so much space. It's just swap again. So that's again big O of 1. And when it comes to quick sort, it's basically the same, that is big O of n log n itself. So it's basically the same thing given here. But you won't expect space complexity most of the times, but these are something it's good for us to know. So followed by this, the next thing we basically need to know is that there are some other sorting techniques as well. We use different methods. There is counting sort, radix sort, and bucket sort. So if they ask you whether these are the only sorting methods, no, there are others. There is counting sort, radix sort, and bucket sort. So the way they work is, in short, again we'll not go in depth within this. In short, here's how they work. So in a counting sort, every element in the range 0 to, let's say, k, for example, it has to be within that range, and you should know that. Then you can perform counting sort with worst case time complexity of n plus k, n plus the range of the variables. So if it's only 0, 1 and 2, it's n plus 3 and so on. But in real cases, when we take much larger examples, real cases when we take examples of hundreds and thousands of elements, it's one close to n log n. It's much larger than that. That's why n plus k doesn't seem it, even though it seems like it's closer to n, in reality it is not. So this is the basic idea. And for you to take, there are k elements, or in other words, since the range is from 0 to k, the worst space complexity you need is again k. So followed by this, then the next thing you have is something called a radix sort, where if n digit number is given, where in this case, to understand this in short, let me just point this out so that it's clearer to understand in short. First, let me just explain back with the merge sort. When we talk about merge sort, we just need to know a couple of basic things. I'll just explain this in short, not to take a long time. So both merge sort and quick sort, both of these are divide and conquer techniques. They divide your array into a smaller set of array and they conquer that, or in other words, they only try to sort that, then they go for the rest of the array. So this is basically how merge sort and quick sort. So to understand this in slightly more detail, merge sort has a function called merge, where it will take smaller arrays and it will divide your array into smaller parts, individual elements. Like say if you have an array of 1 2 7 3, it's going to divide it into, let's say, 1 and 2 and 7 and 3, and this again is going to divide into 1 2, let's call it as 7 3. Now these are going to get sorted, which will create back 1 2 itself. These are going to get sorted, which is going to create back 3 7. Then these are going to get sorted, which creates back 1 2 3 7. So to perform this, you need to find an element where exactly you need to divide it. that division is hugely important for us to work through this. So I will not be going through in depth about this. For now, let's just assume you can divide it easily even in half and perform this. So we are basically dividing and conquering. Whereas on the other hand, when you talk about quick sort algorithm uses a particular element called a pivot element, which can be any element within your entire array, and from there all the values are going to get sorted one space at a time. So for example, if you take the last element generally as pivot element, for example, everything before that can be partitioned into a separate array. So there are many other ways to work through this and so on. So going ahead from this, there are other ways which I'll just explain. These are not common ways, but you can expect them to be asked in interviews, because common sorting algorithms most of us will know. Whatever are uncommon, whatever are slightly different, are often asked. Let's take, for example, counting sort. Let's try to figure out what exactly is counting sort and how it works. Example, you have an array from range 1 to 8. So you have values like 1, 4, 1, 2, 7, 5, and 2. Let's say these are the values you have. Now, if you know that your range is from 0 or 1 to 7, if you know your range is from 1 to 7, here's what you're going to do. You're going to create an array of indices, array with index 0, 1, 2, 3, 4, 5, 6, 7. So instead of 0 to 6, 7, you can also consider 0 to 6, where whatever in the value you're representing is plus 1. You can consider it like that. Or even if you have 0, simple easier example, let's take this. How many times is 0 present? 1. The value of it. This is the index. This is the value of that index in the array. How many times is 1 present? 2 times. How many times is 2 present? 2 times. Again, how many times is 3 or 4? 3 present no times, 4 is 1 time, 5 is 1 time, 6 isn't present, 7 is present 1 time. Now that you got to know this, you can easily start printing the count in the right way. So you can also modify the count such that it is easier for you, but in short, think of it like this. So with this, you'll be easily able to get to print the number of elements. So since you have to go through, if you have n elements, if you have range is k, if your range is from 1 to 7, you need to go through this so many particular times. That's why it's n plus so many range based times. So let us move ahead from here. Followed by this, there are other methods as well which you have, including a radix sort as well as bucket sort. So these are also often not asked so much. There's also so many other things like shell sort, tim sort, and so on. So the basic idea I'll just provide, not in detail because you won't be expected to know the code in interviews. So the basic point you just need to know here is, let's say for example, you want to work through bucket sort. So when you want to work through bucket sort, the basic idea is you need to create some, let's say, n empty buckets. When you create n, and I'll just point it out, it is often used for floating point values rather than just integer values. So each element is inserted into a bucket. So if you have values from 0.0 to 1.0, so you will create a bucket for 0.0 to 0.9. Let's say another bucket for 1.0 to 1.9 and so on. So in each bucket you have certain values and you're going to print the values on their ascending order. So since you're going to need a lot of different values to be stored, a lot of extra memory to be stored, the entire space complexity will also increase. Since that's going to be n elements, your bucket sort is going to require at least, or at maximum, you can call it as big O of n. Similarly, the worst time complexity you can expect from this is big of n square as well. So finally, followed by this, you have Radix Sort, where again you need a value k, but this time instead of big of n plus k, this is n into k. And this also requires a huge amount of memory, that is big O of n plus k. This also requires extra memory for storage of elements. So there's not much that you can expect out of only sorting. They may not to write the code, but you just need to know what sorting algorithm works in what and what does it exactly store. So going ahead from this, there are other couple of concepts again followed by this that are called divide and conquer and greedy algorithm and backtracking algorithm. So if you say I know algorithms and they ask like what are the different kind of algorithmic techniques that you know, then you should at least know a few of them. Let's say divide and conquer, greedy, backtracking, and so on. But what? How do they work? What do they do? So in short, is for instance and conquer. I'll just take a very small example that we took earlier. Remember binary search. We could perform binary search as long as the array is sorted. If the array is sorted, we can perform binary search. Let's say 1, 2, 3, 4, 5, 6. Since it is sorted, I can go in the middle and search. If I'm searching for 6, I can skip these 3. I can only search on the other side. So I'm dividing and conquering only one part. I don't need to go through rest. I'm not going through linearly entire array. So I'm dividing this array and conquering only one part because the other is of no use to me. So this basic concept is called divide and conquer. So there are a lot of algorithms that often use divide and conquer technique. Like here we saw a couple of sorting techniques use it, but the most common example is binary search, which uses it, whose worst case time complexity is big O of log n, which is much lesser than linear search, which goes through all elements in worst case, that is big O of n. So followed by this, the next thing that you have is something called greedy technique. So as the name suggests, the algorithm is greedy. Like what it means is, in short, there's not much complication about it at all. So let's consider the concept of global maxima and local maxima to understand what is greedy technique. So let's say the program is to find tallest hill. The program is to find tallest hill. Now you're, let's say, here. So there's one hill here, and after that there's another hill long distance away. So you're not able to see this because it's too far away, but it's the global maxima. This is the tallest hill. But since you're here, once you find the closest hill top, once you go there, you will see no matter which position you're going down itself. You're not checking every part. You're seeing like everywhere else I go, I'm going down itself. So this must be the local maxima. So you'll say that this is where I'm stopping because this is where I'm finding the local maxima. So the point here I'm trying to make in terms of greedy algorithm is it doesn't necessarily find best solution always. It doesn't necessarily find best solution always, but it finds a solution very quickly. The point is to find a solution quickly, but not the best solution overall. So the problem that it suffers with sometimes is that it finds local maxima values instead of global maxima values. So this is the core concept of greedy algorithm. It's greedy in such a way that the moment it finds a good solution, it's like I'm done, I've got the solution, that's end of it. So this is the basic point of it. So in the algorithms, there are some things like knapsack algorithm, and there are two versions of knapsack algorithm. One is fractional knapsack algorithm. Another one is called 0 bar 1 knapsack algorithm. So the 0 bar 1 knapsack algorithm is an example of, I'll just point this out, it is an example of dynamic programming, whereas the fractional knapsack algorithm is an example of greedy algorithm. So the basic difference between fractional and 0 bar 1 knapsack algorithm is the fractional algorithm let's say for example and you want to put in some let's say there's something of and 4 kg, so you know that only 4 can be, but fractional algorithm thinks that fractional knapsack algorithm thinks that this 4 half of this, or it can also say that I'm going to put 2 of these, that makes it 4, 1/4 of this, which is practicable in some cases, but this is what your fractional knapsack says, and it finds one solution. Whether that solution is the best solution or not, it's not for us to know, but it finds a solution. That's the major point. So here, for example, if you have something like 2, 2, 4, and you have already found a solution, like I'm going to take 2 and 2, and I'm going to take 1/4 of 4, then going ahead to check whether 5 can be fit in it or not. So this is the problem with fractional algorithm. Whereas if you go for 0 bar 1 knapsack algorithm, that basically means each object is either not in the bag or the object is in the bag. You either put the object in the bag or you don't put the object in the bag at all. There's no halfway through it. If I put 2 and 2, I'll only be able to fill 4. If I put this 4, I won't be able to fill anything else. If I put this, I'll fill it entirely. That's how bar 1 knapsack algorithm works. So 0 bar 1 done by using dynamic programming, whereas greedy uses fractional knapsack. Now we won't be able to go through the entire algorithms, of course, because going through each algorithm will take a minimum of an hour and a half for us. So I'm just taking 1 or 2 examples for us to understand with the concept of what exactly are these algorithms. So I'll just point it out. Divide and conquer algorithm technique. It divides the given data at a time to find the solution, whereas greedy finds the best, finds a possible solution immaterial whether it's best, and this is often called local maxima problem, because even though there is a global maxima few steps away, it won't continue. The moment it's find a possible solution, it stops at local maxima once found. So could or it could not find a global maxima. That depends on the data set, that depends on the input and so on. Then finally the last thing that you have is dynamic programming, which we got to know with examples, and followed by this you have something called backtracking. Now as the name suggests, backtracking means to track back, as the name suggests. Think of this. Let's say you're going into a maze, and in this maze you're supposed to find the end of the maze where let's say there's some reward. So the moment you enter the maze, the first thing you're going to do is say you go left here. So once you go to this direction, let's say for example all of these are dead ends, once you go here you again find 2 possible solutions here. Let's say you go to the right, you see a dead end. Since you saw a dead end, retrace back to the next step. So in recursion, you go back to the previous function. It's similar to that. Retrace back to the next step, go try the other one. If also dead end, retrace back to the previous step. Sorry, not next step. From here, this is a dead end, so retrace back to previous step. Go to the next step, it is dead end, so retrace back to previous step. Go here, this is done. Now retrace back to next previous step. From here, instead of going to this direction, go to another direction. That's how you find the reward. So at maze, once you find an end, you retrace your steps back and go to another route. You don't just sit there thinking that this is the end of the program. So this basically is called backtracking problem. A very common example of this is n queens problem. What is this n queens problem? It's where you have an n cross n. I'll just give this one example. It's where you have an n cross n. Let's just take, for example, let's say this, a 4 cross 4 box where you have a certain set of queens. So in this, you have, in a n cross n, you have n queens. In an n cross n, let's take one example, you have n queens. So what you need to do is, these two queens can attack each other. I need to move them. So I can move this over here and this over here. Now, no queen can attack each other. So this particular problem is called, let's say, for example, n cross n. So the same can be performed using backtracking algorithm. Backtrack each movement. So another example that is used here is the maze example that we took up earlier. Such maze example are often given in programming as maze examples are often given in programming as a matrix with ones and zeros. Wherever there is 1, that means there's a path. Wherever there is 0, that means there's no path. So when you see that all of these are zeros, let's say for example, there's no path over here. So it goes all the way, let's say here, since you can't find it, backtrack all the way to the previous turn, wherever that previous turn was made. Instead of there, make another turn. So wherever that could be. So similarly here, keep going to find, let's say 0 here. If you go here, go to the previous turn that you could have done, go over there, and keep doing this until you find the solution. This is often an example of backtracking as well. So I'll just give you one example. There is n queens problem or maze problem. Now, followed by this, another common concept in which you can expect a lot of interview questions is computer networks. Now, let's just take a look at computer networks in terms of what are the kinds of questions you can expect, what you know, and how can you easily answer them. So whether you're from IT or non-IT, this is kind of an important domain, because when you do any projects, whether you're joining in as a non-IT student, particularly from electronics or electrical branch or anything else, when they ask you about your own domain stuff, you can answer anything such as, let's say, IoT projects or whatever that is you have done. So in that case, you need to learn what are the possible questions you can expect in the computer networks and what can you answer according to the same. So let us try working through the same. So first thing that we should always know when we talk about computer networks is the first basic kinds of question you can expect. The only common question, whether it's from interviews or from exams, that you can expect, that is called OSI layer. Let's try to figure out what exactly this is and what sort of questions do we get. So OSI layer stands for Open System Interconnection Layer. So in this open system interconnection layer, you have 7 particular layers, and these 7 layers are where you can expect questions from. So if you say that you worked on networks, they'll start asking you what is OSI layer. Then your first response is to explain what are the 7 layers in OSI layer model. When you start explaining the layers in just stating the layers in OSI layer model, it's obvious that they will ask you to explain one particular layer, how it works. This is a common thing. So let's just look at this in short, not in much detail, because uh, it's not expected for us to know so much, but we should know enough so that whatever question is asked, we should be able to answer. So there are 7 layers to begin with. We'll start with the first one, that is application layer. Now, first, let me explain what exactly this is and how it works. Let's say you are receiving this video. You are receiving this video from a YouTube server. So, YouTube server sends the data in a certain way where you receive it in your system. So, when it is sent through OSI layer model, OSI model layers, 7 layers, and it is received through the opposite layers. So through OSI layers, data is converted from its software bit form, whatever it is, into electronic streams. In reception, when you receive, it is received as electronic streams and converted back to the format which you can play in your browser video or a browser video player or anything like that. So similarly here, in one example, let me just take, what if some network connectivity breaks down in between? How will you get to know where exactly network connectivity broken down? How will you get to know which second the video got paused? That is all because of OSI layer. All of this reconnection of network, once reconnected, what byte should I receive again? What byte was missed out? How to keep track of it? How to keep count of it? All of this done is basically done by using OSI layer. Even when you access youtube.com, its access is also performed through your web page, through your HTML page, whatever it is, by this layer. So let's just go through the layers that we have in OSI model. So the first or topmost layer we have is called application layer. As the name suggests, as the name states, application layer is an end user layer. It is the end user layer. It is the layer which is visible for us on screen, on computer screen. So for example, we have all these things like FTP, HTTP, SMTP for mail transfer protocol, and DNS, SNMP, and all these sort of things. So if you're accessing a transmission protocol, file transfer protocol, or a hypertext transmission protocol, transfer protocol, or whatever it may be, whatever you're accessing, all these protocols, they are part of application layer, which help you to figure out how to show something on the screen to the user. So what format should I show it in? What application should I read it in? And so on. This is done by application layer. If I receive a web page, I'm supposed to show it in a certain way. If I receive a mail, I'm supposed to show it in a certain way. All these protocols, these rules, how we're going to show all of this data are taken up by application layer, basically. Now, then comes presentation layer. Presentation layer is also called syntax layer. Now, first, I'll explain only from the point of view of a sender. From a sender, what exactly happens? When we talk about sender, not receiver, the first thing is it goes through application layer. So if I want to send something to someone, if I want to send, let's say, a WhatsApp message to someone, I am sending on an application layer through a protocol which will convert it to some other format and send. So this is my end user where I can see that particular data and layer, data and everything are basically, let's assume, as application layer. Followed by this, presentation layer, whatever particular format the sender sends in, whether sender sends a video, audio, HTML page, whatever it is, whatever it may be, presentation layer converts the sender specific format into a common format. This is the work of presentation layer. Whatever sender sends, that specific format is converted into a common format. So once this is done, the other work is to also ensure that this common format is available at receiver end to receive this common format and convert it back to that receiver specific format as well. So there are a couple of things that are done here. So one thing is compression, another thing is encryption. So it compresses the data, so the number of bits to be transmitted are reduced. Also, it encrypts it so that only user can read it and convert it back to the form. So what is encryption here? The point that it converts sender specific format to a common format to a different format is basically encryption. Because even if someone in middle sees it, they will see this format, not the sender specific format to read it. So that is the encryption part here. So from application layer, if I click send, it's going to go to presentation layer where it's going to get converted to a different format. Once it's converted to a different format, then comes the next thing, that is session layer. This is the third layer. So session layer, the major work of it is to ensure that it is able to connect to the other device. It adds something called checkpoints. So there are two major things that it does. So from here, whatever data you're sending, the major part of it is, if somewhere something goes wrong, should the receiver receive back from first byte? No, the receiver should receive back from the byte that the receiver wasn't able to receive, where it was lost. So session layer establishes a connection between sender and receiver. For example, you guys may know, whenever you download a file from a website, it may say this file will only be available in this IP link for 1 more hour, or this file may be available only within your session for as long as you have logged in. So since you have logged in, you have created a connection between sender and receiver. The moment you log out, you won't be able to connect to it to download your file or receive your file anymore. So that is exactly what session layer does in short. It creates a connection, interaction, or establishes a connection between sender and receiver, due to which you can send the data and receive the data. So while it is sending, while these processes are communicating, so with session layer, two processes communicate. So one is at sender part to send the data, and receiver part to receive the data. These two processes communicate here to ensure that, hey, I am logged in, I want to receive it, and the sender is like, yes, I know you are logged in, so I am sending the data. So followed by this, the next part is that it also ensures, followed by this, that there's something called synchronization and recovery. So the basic point of synchronization and recovery is to add checkpoints. So just like in a game, whenever you lose a game, you lose in a game, let's say computer games or something like that, you are sent back to the previous checkpoint. So same thing goes here. The moment some data is lost, it doesn't restart entire transmission. Whenever transmission is lost, it reverts to last successful transmission checkpoint, and it will start transmitting from there. That is basically its work. So till now it sounds pretty simple. Now from here, the next thing is called transport layer. So till now whatever we did, this is more of an application level. This is more of, you can say, on the level of application side. The rest comes to network and hardware side as we keep going down. So this is purely an application level, which is converted and encrypted, where you get a login session connection and so on, where checkpoints are added, so you can recover data transmission in some cases. So followed by this, the next thing is transport layer, where you have a lot of different protocols working here. There are two major protocols that we use here. So in transport layer, data is divided into segments, and each segment is transmitted at one after another. The major work of this is to divide the data into segments, and to send the data as segments, there are two protocols that we use. One is called TCP, the other is called UDP. So TCP is also called Transmission Control Protocol, and UDP is also called User Datagram Protocol. So the problem here is, in User Datagram Protocol, although it is faster, because the reason it is faster is because it doesn't save checkpoints, it doesn't store extra data or so on. So because of all these, it is faster. But the problem is, since there is no checkpoints, no all these sureties, there is no guarantee of data delivery. Also, there is also no retransmission option from checkpoints. So these are the problems that we face in User Datagram Protocol. So in some websites, you may see that there is no option to download again. The moment your download stops, you won't be able to access that link ever again. So that is generally done using UDP. Whereas in TCP, we generally have these checkpoints, everything is saved, and there is delivery guarantee, there is error checking, as well as retransmission of lost packets. Whatever data packets are not sent properly, they can be retransmitted. That is the major idea. But because of all these things, it is slightly slower as well. So these are the two different things we need to know. So now that we got to know this, let's try to figure out what exactly transport layer does. We got to know there are two protocols in it, in which we can use either one of them. So here's what it does. So transport layer divides your data into segments. Segments is the data format. From now on, every layer has its own data format. So transport layer has a data format called segments. So each segment is with a unique number, or you can say token number or something like that. So every segment consists of a unique number when sending. So when sending, since it has a unique number, this sequence of unique numbers, it is always in a sequence. This sequence of unique number are preserved while sending data. This ensures that data is sent in the flow from first byte to the last byte in the right order. It's also called flow control. So followed by this, there's one more thing that it does, that is, it ensures that if there are errors, it'll check and make sure that it'll be able to retransmit the data. How does it do that? Any segment, any sequence in this unique number sequence, if any number is missed out, the receiver gets to know that this particular number is not received. The receiver can ask back for that numbered segment and receive it again. So this is also called error control. So flow control and error control are the two major functionalities in transport layer. Now followed by transport layer, the next thing is network layer. So once transport layer divides it into segments, it needs to send the segment somewhere. It needs to send the segment somehow. The way it sends it is through network layer. Network layer takes segments and divides it into packets, or repackages them, in other words, into packets. And these packets are sent through IP addresses. So, for example, I have an IP address, you will have an IP address. From my IP address, these segments are sent over to your IP address. But we need other layers to send. We just can't send from IP address to IP address. We need physical connections, we need wireless connections, satellite, something. We need some other things. But for now, to identify whom to send, we have something called IP addresses. There are two types of IP addresses, that is IPv4 and IPv6. In the future, most systems will only have IPv6. IPv4 will go out of existence unless a lot of sub networks are continuously created. Even right now, IPv4 are limited because they are only 32-bit long. For example, 125.5 0.0.1 or 128.0.0.1 or something like this. So they're only 32-bit long, and there are only limited addresses that you can build out of these. So most of the times, subnetworks are created to ensure that there are enough IP addresses to go around. So apart from this, the subnetworks are basically where, let's say for example, there are limited set of IPs around the world. So what is done here is, so I'll just try to explain this. All right, perfect. Now that it works. Subnetworks are like this. Let's say you have an IP here, and this particular IP is, let's say, 152.1.1.0 or something like that. And under your IP, you can create 3 more IPs. Let's say, for example, and these 3 IPs are only visible to you, not to the rest of the internet. To the rest of the internet, they can only see you. If there are 3 computers connected to your system, these 3 computers will have IPs connecting to your system. Your router here will know which system is connected, sending a message to you, and to which system you're supposed to send a message back. Here also, which system is sending a message to you, and to which system you're supposed to send back the message. But when you send that message over to internet, let's say both of them are accessing Google for different search results. One is searching for networks, the another is searching for, let's say, something called computers. So it will know that this is the device which is searching for computers, and this is the device which is searching for networks, because this router knows which system is sending which request, so that it can give back the same response. And when it is searching for networks and computers together, you will get to see that, or Google will get to understand that only one person is accessing multiple searches. So this is why most of the cases, when you look at universities, if they have a single IP address which is divided everywhere, even if you search something, even if you go through a certain website and they ask for CAPTCHA, stating that you have visited this website too many times today, that is why we need to confirm whether it's you or not. It's not because you visited in your phone, it's because your IP router visited. There can be 100 other systems who visited the same site. Since it visited 100 times today, it reached its trigger. You're the 101 person. So that's why you get captured to prevent DDoS attacks and everything. So these are examples of how these things work. So instead of 32 bits, 32-bit IP addresses, you can also create 128-bit long IP6 addresses as well, lengthier and can take up much more systems. You can have much more systems together. So something like this, FEA0, let's say for example, all of these will be hex, like D4A. Again, I'll take D4A6. So there is 3 of them. take a little more. So like this, if you can keep writing, you'll get to 1 GB. So this is how V6 address are stored, followed by IP addresses. The next that mainly network layers do, is to send data to the right ports, because in your computer each port is for something specific. For example, generally we have 05536 65535. So ports, all of them, let's say 02 1023, are often by for specific purposes, SQL, MS, followed by 1029 1150. These are general or registered ports. These ports registered by any software to use. That means your downloading software can use it, your browser can use it, any software. Whereas finally 4152 26553, these are called dynamic. These can be used for at any time. So for example, we generally register 8080 port to access something within some IP and so on. So under IP, we also have so many ports which we act for different purposes, and under these we always have rules called protocols for sending and data. So other thing that network layers also does is find the best route to go from source to destination. That is called routing. If you want to send from a server in Mumbai to, let's say, a server in Delhi, you try to find the best possible route to do that. You don't go send the data from Mumbai server all the way to some Pacific's California server and then get back to Japan and then back to Delhi. There's no point in that. So you need to find the best route to go from source to destination. That is also done by the same layer. Followed by this, the next layer you have data link layer with 2 layers again. This is divided into 2 layers. That is logical link control layer and layer called media access control layer. So here's what they do. Logical link control layer and media access layer are together responsible for the following things. Firstly, we had segments. These segments had unique numbers. They were repackaged in packets. Now here, when packets are to be sent, these packets are repackaged into something called frames, and these frames sent ahead. And here also the same thing is taken care of. That frames are sent in the proper, and these frames are ensured that no errors are ensured by use like cyclic redundancy check. This in error detection and correction as well for retransmission purpose. Now, in this case, you have 2 parts, LLC and MAC layer connects network layer to data link layer. That means it's put it into frames and so on. Whereas media access control connects data link layer, physical layer. Them have different works. So media access layer will ensure that that is sent in the physical over to physical layer, and the logical link control layer takes all these data which is from and puts it into frames by checking all these things, error control and everything. There is a link layer. So once the data in frames is sent to physical layer, that is your Ethernet cable, through your internet, it is converted to bits. And bits of data is transmitted. So basically, whenever you want to send as data, first gets converted to a format, and that format, to send it to a receiver, you need to establish a connection to the receiver. Once that is done, that data is divided into segments in packets, and the packets will have a link to whom it is being sent, all these information, so that sender and receiver will get to know who should I send it to, because it's not that directly you're sending it from sender over to receiver. There are many routers in between. To all these routers, when they check they will understand who is the receiver, who am I supposed to send it to next. All these data are added in the packet. So it's not just that segments are converted to packets. Segments are there within packets. What is added here are which the source, which is the destination, which are the IP address which it is to be sent, and so on. Because the work of network layer is to perform routing as well. So all of this is performed with packets. Packets are then converted to frames in order to send. Then these frames are converted to bits in order to send over the network. So this is the entire OSI layer model. This is from sender side. When it goes to receiver side, receiver will receive in physical layer as bits, and data link layer, which converts it to frames, and these frames are sent to network layer, which converts it into, it gets to know whether it is the right receiver and everything. Then this is sent to transport layer, which converts it into segment and gets to check whether right unique sequence numbers and all are received. If it is not received, another transmission request sent back to the sender. So once this is done, it is then sent over session layer. Knowing that there is a link established, it goes to presentation layer, which converts this common format to application specific format, which is then to application layer, where you can see the same data. This is exactly how it works. So this is a common question that is commonly asked, which now I hope we can easily answer this. So I'll be sharing this content for your reference right here, so that you can access this later on as well. So moving ahead from this, other things you guys should go ahead with as well. Go through as much as to ensure that you guys are going through as much content as possible. So I'll be link over for intensive program to replace Infosys